Okie dokie, welcome back you guys. Hey, we're back for round 2 in our population unit. And it's going to be a shorty. Alright, you guys will appreciate that on your weekend, but shorty but a goodie. Alright, so we spent some time in class just the other day graphing human population over time, right? And we should have seen a pretty distinct shape. Look very similar to what we see right there in that graph, right? And so one of the things I want you guys to understand is populations grow exponentially, right? And that exponential growth has a characteristic shape that we call a J-curve, all right? And during that period of time, when they're undergoing that exponential growth phase, it's often referred to as the biotic potential or the intrinsic rate of growth. So the maximum growth rate achieved when ideals are good and populations just kind of skyrocket like that, that's what we call that. Okay, so growth rate under ideal conditions, the maximum growth rate, we refer to that as the intrinsic rate of growth or the biotic potential. So really important vocab terms there. Okay, and we recognize the biotic potential or the intrinsic growth rate as that J-shaped curve that we're getting familiar with. All right. But we should understand that, of course, that growth cannot just continue indefinitely, right? That J-shaped curve is going to have to meet some sort of resistance because of space or food availability or all of the above, okay? So we have environmental limits that put a stopper on that biotic potential or that intrinsic growth rate eventually. Okay? So our environmental limits or environmental resistance, often referred to, it prevents that indefinite reproduction. All right? And that takes the form of, just not being enough food to sustain a population or water or shelter or predators or space. Okay? So those are what we call environmental resistance. And when the population meets environmental resistance, right, our exponential phase of growth starts to take on a different shape or a different form that we refer to as logistic growth. Okay? And so eventually a population will begin to level off. So we have our exponential phase that we see in our J-shaped curve, right, on this portion. But as environmental resistance comes into play, we begin to see our population level off. And that is that logistic growth phase. All right. And eventually kind of sort of leveling off around that maximum sustainable population. And that's what we call a carrying capacity. So basically when a population size kind of levels off and it hovers around this point here that we call the carrying capacity, that means that that environment can sustain long-term a certain number of individuals, and that population that can be sustained long-term is what we call the carrying capacity. All right? And so the exponential phase is that J part of the curve, but the S curve we see shows a logistic phase and then an eventual leveling off at that carrying capacity. All right? Now, occasionally, there are certain types of populations that will overshoot their carrying capacity. And so sometimes if an ecosystem is thrown out of whack by, let's say, maybe some predators die off, right? Predators are really important because they control populations of prey, right? And so in the case of here, we can have a prey species that's usually an herbivore, and the absence of a predator can overshoot that carrying capacity. And what happens is their population becomes so large that they deplete the food supply, right? And then rather than maintaining a smaller population, they get a really large population for a short time, they deplete their food resources, and it results in ultimately in a big, massive die-off. So this is, for most populations, this is an unhealthy population curve, right? So again, we would like to see this population level off at its carrying capacity. Here, we overshoot that carrying capacity and we get a resulting massive die-off. Now, for most populations, that's unhealthy. There are some where that's a natural cycle, and we'll get to some of those examples in just a little bit. All right. So one of the types of factors, I should say, that affect population size are what we call density-dependent factors. And those are the things we kind of talked about already. So density-dependent factors are things that whose effect on a population changes as the population density changes. Right? So predators, right? The denser a population, the more effect a predator can have, the more effect disease can have, the more effect competition for resources can have. So these are things that increase their effect as the population density goes up, right? And these types of things can sometimes cause a boom or bust population cycle. So again, this population growth curve right here, I said, is unhealthy for most populations. There are some who naturally follow that cycle, and lemmings are an example. All right, so lemmings go through these boom or bust population cycles. It's just part of their natural evolutionary process over time. So there's periods of time when there's a really high population of lemmings, right? Those density-dependent factors take over, and that population plummets. All right, and that decreases the effect of those density-dependent factors, so that population skyrockets up again, and then they take over, and then it skyrockets up, and then they take over. That's a normal population curve for lemmings specifically. So it's, like I said, some populations have naturally found ways to cope with that, but most populations, right, we want to see a curve that kind of levels off, right, around that fixed point. That would be our carrying capacity. Some populations just do this boom or bust cycle. All right. So moving forward to human population, as it were, right? So we know that human population is still, or is currently undergoing its biotic potential or exponential growth from that J-shaped curve we just graphed the other day. All right. So demography, by the way, it's a science of population structure and growth. Right, so demographers are the people that study human populations and population dynamics and how they change over time. All right, so since 1800, we've been going through its J-shaped exponential increase, and again, we talked about that in class as being due to advancements in modern medicine and so on. So the death rate decreased dramatically as a result of that. Okay, and so looking at our human population over time, we can see, all right, the amount of time it took to increase by 1 billion between 1800, so it was 130 years there, whereas it only took, about 12 years to increase by 1 billion later on. Okay, now projecting future populations, you guys have been introduced to some math, right, for that, and so if we assume a certain growth rate in the future, we can then project that population. Okay, so different demographers have agree on different potential growth rates in the future. So we have our current growth rate that's not going to sustain forever, right? So that growth rate is going to decrease at some point. So there's a range of projections for where we're going to end up around 2050, and those range from 7.7 billion, which we're actually already almost to, all the way up to 10.6 billion by the year 2050. Most likely, based on current projections, we're going to end up around 9.8 billion. But notice that all of our projections have us at least beginning this logistic growth phase sometime during the century, during mid-century. So growth rate is going to slow down. At some point, the human population is going to stop growing. That is a fact. Now, where exactly we level off and whether that is a sustainable population is a question. So which will it be for us? Will the human population overshoot its carrying capacity, run out of things that help us produce extra food, like oil, coal, natural gas, or will we level off at a sustainable level and live happily ever after? All right, that's the big question. There's a lot of variables involved with that we will talk about the next time I see you. Love you.